So who's heard of Moxons? Quite a lot of you. I just want to say, because you guys seen a lot of VHF, UHF antennas. You haven't seen the whole gamut. But I'd like to talk about a couple of other ones that you may not have heard of, although most of you probably have, but some people watching may not. So I'm not going to do corner reflectors, zigzags, helicals, Helicals today, but maybe next time. So let's start with Mr. Moxon. He basically got his idea from Fred Caton, VK2NO. Has anybody heard of Fred Caton? So back in 1973, Fred Caton got a Yagi Udason antenna, and he wanted to make a square one because he had a space issue. So he folded all the sides in and made it square, and then he separated it with buttons, big coat buttons. And so it didn't work out quite well, didn't have enough gain or anything like that. So Les Moxon picked up on that. Now, Fred Caton did this in like 1973. Les Moxon picked up on it around the early 90s, 91, 92. And he thought, well, I'm going to get a Yagi and turn it into a rectangle because it's not going to have that much loss, actually. And you can see from here that it's quite a simple antenna. So if I draw one here, it's has a parasitic reflector, like a Yagi antenna. And it's a very simple thing. Some people do extra things. Some people make a 3-element Moxon. Anyone heard of a 3-element Moxon? Yeah. They actually put another element down here. Sorry, that's all very straight. They do something like that, which is interesting, and some people like to put more on there to get a bit more direction, because you've got the where you feed it in here, and the direction is here. The reflector points it this way. And the reflector's slightly longer just so they can handle the phase differences. That's how they usually work on those things. So this one picks up all the transmission, points it that way. Now, other people have done different things with Moxons. It's magnetic, that's pretty good. Some people do multi-band Moxons. So they would have, you need a brace, and then they start to add bands like that. So you could, for example, have a 10, 6 and 4 metre Moxon all on the one pole.
Separate feed?
You can do separate feed if you want, but I've heard that you can use a straight feed. You don't need traps or anything, it just finds a frequency you want. That one goes down there. Now it's a bit rough, but you get the idea anyway. And the other thing that some people do, a lot of rubbing out. Some people stack them. So they may have then another one underneath. And we can have another one under there like that. Just to give you more gain, they say. So your pole, you have a small pole now, big going in.
Or you can have different size, different band Moxons.
Yeah, you can have different band Moxons. You can have a 10-6-2, you can have 6-2-70, anything like that. And they work quite well. So I'll go back to the standard Moxon, because today I'm going to show you how to make a pretty standard looking Moxon. Draw that a little bit better. So you have a separation in there, and I'll tell you about that shortly. So I started modelling one up in the neck. It's pretty straightforward, easy thing to do for these. You can get a whole library here, see it online, go like fiber. But then I had to modify it for the size that I wanted. And I wanted to test whether the size would work or not. That size that I came up with, because I wanted a portable one, gave me that kind of, see the beam with it, it's very generous beaming. I think they're actually better. That's better than the radio. It's more broader. It's not critical when you're going to aim your antenna. And you can see the reflection line there. It's straight enough to write a linear equation for that. It's so straight. So I thought, is that really going to work? So I thought I'd make one.
So that's in the same line.
That's in the same one. So this is very portable. Moxon. Very easy to make. I use some junk there from Moxon space. I might get my radio out of my bag.
What's in the middle of the top?
This is too short.
Oh, I see.
So I needed a bigger piece
Right, okay.
just to hold it together. Sometimes you can't
What,
get
was a resistor or something along the way?
Zero.
I couldn't resist putting it.
A zero.
Just bring my bag up. I'll just put the radio. Bring the radio on. So I wanted something so lightweight and portable. Hasn't come to the rescue, but I forget things all the time, like this is my car, except and it just sits on top like that. Now, because it's driven element on a reflectors like that, it's going to go that way. You could have it that way if you want. In fact, the ones that you want to do 3, 10, 10, 6, and 2, if you want to build those, you can have them vertically, or you can have them horizontally.
But that's just bits of dowel, isn't it?
That's just bits of down. So I think the rest of it's the element. I'm probably not going to ping anything here. This is a Faraday cage, isn't it?
You'd be surprised. Try the local one.
What's your typical game?
About 16 room.
It's pretty good.
Getting something. That's good.
That's the idea of the March papers.
Yes. I'll just stick it out there, I'm sure I'll get it. I might do that. So this is a very easy thing to make. You might want to use thicker metal so you don't need a dowel there. I originally had a chopstick on there. You can also do a 3D mount. 3D printed mount. I'll probably do a nice little triangle mount there. Which will work out this a bit more stable. In case anybody wants to know, so it's 74 centimetres, 15, 10, 10. So if anyone wants to make this sort of, I had this sitting on my table, I hadn't even finished it. I pinged into the Summersmead, and I'm at water, and I rarely get into Summersmead as it is. So, and also with this, okay, you need a dowel, right? You need a dowel to separate the parasitic from the driven element. Now the dowel itself, it's got a bigger version of it here. You want to go in 1 centimetre that way, 1 centimetre that way, and leave 4 centimetres this way.
Critical? Or you just need an air gap?
You need an air gap, and it's somewhat critical. I tried in net to have it more separated, and I have different plot readings, of course. I have the SWI going a little bit. So I found this was the ideal sweet spot. So all I did was I got the dowel, put the drill in, and then you had it with 10 mil sticking out, so you knew how far I was going. Undiscluded in. So
But the long driven element is reflecting.
it's a reflector. Yes, parasitic reflector, just like an average.
So it'd be better if, rather than just put it on your radio, because you're holding the radio.
I know. I've had this sitting on a tripod.
Yeah.
I've got it in Summersmead on this outside,
Yeah.
sticking out of the radio.
Yeah.
I thought that was a really real ripper. I thought it was really good. But let's when I first made it, she put a chopstick in there. I'm going to call it chopstick. just to keep it sort of in shape. But you can see the reflection curve on there. And that's pretty good on the VNA. I'm quite happy with it. I forgot to put the Smith in there, but the Smith fits pretty well with the small 2 months left on the middle. So the middle is the area that you want it. So I was really happy with that. That worked really well. But yes, you can put that on tripod. I've had a little tripod on my desk. So, cable coming up to the radio. It works well, it's rotated or whatever. That's how it works, I'm very happy
So
with
it's
it.
actually it's actually firing towards the connector.
Yes, it is.
Yeah, so you probably don't want it when you're
Yeah, that's what I was thinking.
yeah.
Well, I'm using 5 volts on this.
Yeah, I know.
I was thinking the radio.
This
No,
handle.
don't worry about that. I'm just thinking that, you know, if you have it like this, you know, like this, it's a kind of waste.
Oh, I know. That's why I have it on something else.
Yeah.
Like a tripod or something like that. But if you want to go portable, it still works very well because the bandwidth is really, really generous. So, there you are, just
Yeah.
hand it around if you want.
Yeah, we don't.
Customer.
Yeah,
So you can use cheap towel, you can use thicker metal, whatever you want.
Never mind. What I'm thinking, because you're holding this, it's basically going into the radio, direct swinging into the radio. If you reversed it and used the outer link as a breakdown,
Yeah, you can do that.
in that way you're not going to
Now, I
be,
thought about making a ring for that sort of thing.
instead of a driven element reflector, driven element director.
That's right. That's right.
And then if you have all the right position for you, you're a reflector.
No, I'm a pretty good reflector, aren't I? Not saying it, but. All right. Any more questions on Moxons?
Sorry, what was that little central piece there on the?
That's just a joiner.
It's just a joiner, so.
Zero resistance.
I just got the plastic off it, I don't grow with it. Thinking, oh, God, this is too short, this piece of metal I got from Moxons. So this whole thing cost me $8.
That's fantastic.
$8 for the metal, comes for the dowels. The most expensive thing was the BNC connector, which I got here, I think it was $10 for it. So I got it down to 5.
Yeah, sorry, what was it for, that little connector in the middle of the back?
It's just a joiner. It's just a BNC.
It's just a no, that's on the top.
Oh, at the top, that's only because I got a short wire. All I had was short wire, I didn't have anything long enough that I could bend around.
Oh,
So I had to join it somewhere, I thought I'd join it in the middle instead of the side or something like
You think it's an active part of some sort?
that. Well, I have to say the antenna was really, really well. So I've pinged most of the repeaters around Sydney anyway. So Wollongong, I've got Wollongong, I've got Somerton, got Hornsby, which doesn't always work very well. So there you are. Other antennas. Who's heard of halos?
Yes.
Yeah.
Oh, yeah. Aren't they fun? These came out around late 40s. Some of the older ones were stacking it like I showed you on the Moxon. And that's actually a broader bandwidth on them. But the later ones, they use gamma match on them. Like you can see, you can make them for handhelds. And I saw a handheld one of the last Trash and Treasure. I think about that. Maybe we can track down that guy on Tree Peterson.
So the benefit is direction one.
No, they actually have a normal mode radiation.
So what's the benefit?
Changes.
Makes your carbon better.
Yeah, makes it kind of better. But you can't change that to a loop if you wanted to. That's what story bar.
Right.
The thing is that you can use the halo as a horizontal antenna on a beam.
Right.
Yeah.
Which is what they always used to use.
Yes.
I think some of the authorities have to make it look more official or something. So here's a diagram. Here's another one you can make. That's a very straightforward one for 2 meters. It's got the cooling bar there. It's so-called the gamma match. You can put a capacitor, put a trimmer cap in to start with. You're not quite sure on the VSWR, and then you can take it out when you get it right. But the shorting bar itself, that can move. So that's like a clamp. So clamp. So that's all it is. But the shorting bar has like 2 clamps. And it just moves that way or that way to get your VSWR. And they're quite a good antenna. I've heard they're about 60 meg. Don't know how, so I haven't looked at them because I want to move on with the other antennas. I just want to show you all kinds of different antennas. Okay, any questions on halos? I think,
Variation of that's well.
yeah, that's true.
Have you modelled that
I
design?
haven't modelled that in there. There's something else coming up that I modelled. And I modelled that in that way.
Thank you.
So next slide.
So is that the same as like a loop bearing, like what's known as a loop bearing? It's working on a different principle.
It's not directional.
It's not
So
magnetic.
it's horizontal. If you had it vertical, you might be able to modify the shorting bar, make it a rotating. I don't know. Comments the external. Actually, come on, you know.
But like what I'm doing is, how is that like physically different from a loop bearing?
Completely.
Well, it's not physically
I think it's more the size.
And what
It's not
what
an
you're
antenna.
driving it with?
2 meters.
No, but if you were driving it with HX,
Oh,
then it'd be less than 1/8 of a
yeah, you'd have to make
magnet.
it much bigger.
And then it would be, well, then it would be a magnetic loop.
That's right.
But if you're driving at 2 meters, then it's, just a normal.
It's a normal mode. It's
Yeah.
omnidirectional. And here's another one that you could look up online. These are fun. These helicals are fun. They're easy to make. You can see in the diagram they've got shorting studs in there. They're like bucket slots to
Yep.
make it match. And these are also normal modes.
What are you driving? Are you driving the little loop or the big loop?
The little loop.
The little loop. Yeah.
So those sort of things. That's normal mode.
Is that radiation pattern good for satellite work?
Not necessarily.
Well, where's.
I'll tell you in a minute what is.
Right.
Careful,
That's normal mode. Omnidirectional. The other way of doing helical is axial mode. Goes this way, runs along. For that. Which is what my next slide is. So helix antennas, I really love these. They're kind of crazy things, aren't they? They're mostly made for comsats, high frequencies. A lot of interesting things about them. But firstly, I was going to talk to you about circular polarization. That's what these things are. They're travelling wave antennas.
This is for satellites.
Mostly for satellites. But when John Krause invented it, there were no satellites. It was like 1946. He wrote a seminal book called Antennas, all about these things.
Catch it, dial.
Let's talk about the polarizations. Going from the right-hand polarization. Circular polarization. You could do left-hand circular polarization. Most of them are on the right side because most receiving antennas, vertical horizontal, actually receive those transmissions quite well. But if you have a left-hand horizontal polarized, not so well, especially if you're using a right-hand transmitting to a left-hand circularly round antenna. It's interesting, isn't it? It's just a way to think it. Some government organisations use left-hand polarization because of security or what have you, and they don't want any interference from other antennas. That's why they go that way. Most of them are right-hand.
But if you bounce off a wall, it's going to swap the polarization.
Well, I'm not bouncing it off the wall. I'm only using a reflector. I wouldn't want to use it in here.
No, the bird, yes, of course.
But anyway, okay, can anybody guess?
It means, I'd say 23 centimetres. Where you are in the world, always transmit up right hand, come back down left hand. You don't have to worry about your antenna orientation.
Can anybody guess how Krause came up with the idea?
Yeah, the nightmare.
Somebody wound him up?
Yes, it's leaky.
Yeah, slinking antennas, aren't they fun?
Yes.
They're normal mode antennas.
Down like plastic.
I'll give you a clue. I don't know if I can draw this, but I'll try. So, like that.
I haven't shown you the vibrator before. Having waving, you know. Wave shop. Following 20 minutes.
Talk amongst yourselves and like this. So, this is really interesting. So, anybody know what that is? Anybody heard of a clystron?
Oh, yeah.
Clystron? So Krauss had a friend, Dr. Raines. He went to a symposium on microwave transmitters. And they were usually working with clystrons which had cavities. And then he came up with this, Dr. Raines came up with this, which is a travelling wave electron beam gun. So you got your gun in, you've got your collector here, and the RF goes in, goes out, and acts as a kind of an action. And that's where he got his idea from. And he said to Raines, Krauss said to Raines, I think it's a great idea for a travelling wave maybe from left to right. And Dr. Raines says, oh, it hasn't really worked. Give it a go. And this was in the microwave area. So that's where he got his idea from.
How long ago?
1947. There's another funny story. My father was in the Air Force, and he had another friend who was in the American Air Force who had some connection with Area 51. Because there were no satellites, Krauss's antennas were used in a place called Jackass Flats down in Area 51 Flat Desert. There's on the side of the hill where they built storage room where they put vertical takeoff jets, and they put circular polarized antennas as well. And they used these antennas in the early 60s to talk to high altitude spy pilots and spy aircraft on the Lockheed A-12 they call the Oxcar. And that's what they used. And they had like 30 elements in there, 30 segments. So very high gain. A typical gain on these things would be 15.
Wow, that's not.
But you lose the advantage. You get another 3D with it, 3D on return. Get to the 10th one, the grades, it goes down to 2.5 and goes to 2. But some people still use 30, and back in those days, they had like these things stacked in 30 tons. Pretty amazing. Okay.
Are they very directional? I mean,
Yeah, that's what they're for. They're,
what sort of beamwidth do you think? Well, it's not beamwidth.
it's very narrow. It's a very narrow beam. And I'll do 2 of these just to show a different example. So if you've got a straight reflector, like a circular reflector, standard isotropic thing, there'll be a couple of back lobes, a couple of little front lobes, and it'll be something like that. Looks a bit rude, but there you go. But if you use a conical reflector, this is a whole other area here. We used to do these on real estate, so I know I didn't hear that. So you use a conical reflector, say, like the one I found in the junk pile, you eliminate most of your back lobes, and the thing would be more like this. It'd be a lot fatter. I think that guy needs to see a doctor.
With the same gain?
More gain.
More gain.
More gain. It sort of curves out a little bit, so I think I'm being But anyway, here are the ways to calculate the size of the antenna. Obviously, Krauss, he focused on high frequency. And you need one circumference or one wavelength. Like for microwave, that's fine, very big. If you want to go down a band a bit, you have to get a lot bigger. So turn spacing to a wavelength, like the diameter. You put your half a wavelength, Krauss has said that in his book. Wavelength is in diameter, not in circumference. So if you want to make something from lava bands, you want to, look, that's too rude. So say you want to be really silly idiot, do a 2 metre helix. That's a huge, you're going to have a huge, it's going to be bigger than this. This is to show you, because I made one, that's not even 64, so how do you do it? So circumference divided by pi equals diameter. Very simple. So 2 metres divided by 3.14159, etc. if you wanted to, gives you roughly 64 centimetre diameter. This is about 55, so it's not even that. So you can see here, diameter is 0.94 a wavelength, say, and meters to say 1 wavelength. But we've got to consider pitch. We've got to consider so many things to make this bloody antenna essential. So say this is just the cross section, turn spacing.
You haven't even mentioned velocity factor.
No, I haven't. It's light. It's travelling.
Yeah, all right, okay.
Also pitch. So the pitch, you drop it down. Kraus says about 10 to 24 degrees pitch. That's ideal. So I used Kraus formula to make mine, but I had a look at some of these others. It's not got a good calculator. There's also ANSOF, which is a really good one. But I used MATLAB here. And MATLAB you can overlay more Helicals into the suggested mean cut. It has enough of an elevation in that, so that's really good. A lot of the other ones don't. It's just a model. I didn't want to go full MATLAB. You can see here I circled some of the calculations for a 2 metre antenna. You've got to have spacing between turns 410 millimetres. How ridiculous is that? That's like, that's huge, right? But I found that some of these calculators are just not accurate enough for the lower bands. And Kraus hadn't really considered lower bounds when we did this. So I did make one this size, 5 turns, and it worked. It was just too big, it can't fit it in the gun. So one of the things that Kraus did not consider so much was half wave. Of course you need full wave for microwave. What if you try a half wave at 2 metres, for example? I thought, I tried this, I looked around everywhere, I couldn't find anyone else who's done this before. So it may be a first. So I did not concept. Once I went to Moxon Stratton and got my turn, I did the concept for this. Now, Brad, you can bring it out. I know it's a crazy antenna, but it actually works. Alright.
Oh my God. Oh, at least.
All right. Because they're a project.
What's that? So, lots of mechanical issues. The formulas are easy compared to this.
What frequency is this?
This is 2 metres. This is a half wave that's never been done before.
Oh.
This has not been proper half wave.
In the diameter for each
Well, it's
helix.
Yeah.
yeah.
And there's a couple.
Yes. Yes. So,
Is there another frequency that it?
this actually works on 70 centimetres.
Yeah.
Not so great. Not so great. So,
No.
mechanical issues. Now, I wanted to do a couple of things. I wanted to try doing a removable one so I could just get different assessments in MATLAB by changing turn space and all that. So I was thinking of doing another rail on here, and then that loose on top, go forward or back, and it just makes it unwieldy. But this is possibly the world's only 2 metre.
Or not?
It's the same. It starts at 1, there, 2, so it's an 8 tone.
We're a part of history. We're a part of
It's a part of history. So this is possibly the only half-wave 2
You
metre
applied for a patent?
portable.
Applied for a patent yet?
Another one. But this does assemble. This does disassemble. It actually fit in my car, and I haven't got a very big car.
How long does it take to reassemble?
Not that long. It's about 5 minutes. Oh,
What's the tennis? What's the tennis?
yeah. So some people use metal central support. I didn't want to. Why? Some people. If you send in that documentation, I've read a lot of documentation on these antennas. Some have used central metal supports. I just wanted the dielectric constant was even all the way along. So
That's wood, yes?
yeah, so that's wood.
That makes sense.
These are PVC standoffs, which I had to go on eBay because I couldn't find them anywhere else. They're industrial strength, they said. That's what they said. I could drill a hole through it easily. If I was using little valves like that, say on the Moxon antenna, they'd split. They'd do all kinds of things. So I thought I'd use this. What else? Okay, so the gain, I've got to use a whiteboard to show you the gain, but this is in the way. It's not. But there are other things to consider. One of the fundamental ones, centre of gravity. If I don't have these legs out, it's going to tip over. It's going to go like that.
yeah.
So I thought, well, why don't I make up a radio cradle? Now, this is junk. This is paper towel holder from the restroom.
Take this out.
Once we can. I thought about it getting screwed on. Well, I sort of think of what I want and think of what exists. So it's the 52-metre radio in there.
Yes.
So it just sits on.
Oh, and that gives it sort of balance.
That gives you a counterbalance.
Counterweight.
Oh, wow. Is that got batteries in it?
There's no battery in there.
Yeah.
Not in the radio, I've got a lithium hanging off the
What
side.
frequency are you on? But what, yeah.
I can't get anything in here.
So
Oh, this first, don't I?
So does the shape of the reflector have any effect, or is that good enough?
I think the shape is acceptable. Ideally, I like it wider. You can make it out of any material. Like I thought about getting a big metal aluminum frame and using metal fly screen. And that'll work equally well as long as it was slight conical. That'll work quite well. So that's halfway. But with crowd, the halfway make isotropic reflector is okay.
How did you get on feeding that?
Is there a matching section somewhere?
Yes. So okay, let's go to the next slide. So that's the raw result. I haven't done any impedance matching. You can use a stub or a variable impedance transformer. So once I put the transformer in and put a stub in, so this basically a stub is like a quarter wavelength. You can loop it, you can keep it open, or you can short it. After matching, 2-metre one is beautiful. You can see it on the left there. You can see it's quite a low VSWR. And the 70 centimetres, not so great. And I put a choke on, it's a little bit better. But that worked quite well. I'm quite happy with that thing. Smith is right in the middle, which is just slightly on the capacitance side. But that's okay. I got good results too. I got into Queensland on this. On, what was it, 144, 100. Got into Tasmania. I think most of the repeaters.
Sorry, FM?
FM on the repeaters, sideband.
Oh,
Yes, sideband. I put it for 100. The only annoying thing about 2 metres is there's not many people on it. It's frustration. So maybe I can look for a CubeSat or something like that instead. But ideally, I would, if I had the money, I would have this as a satellite tracking on a gimbal that goes up and down like that and rotates and does it automatically with the frequencies either side, so you can counter the Doppler effect, all that sort of stuff. But at the moment, just having fun on VHF, UHF field days with this thing.
well, it certainly stands out.
Yeah.
You said you got into Queensland and Tasmania with it. Was that direct?
That was direct. I might have been lucky, it might have been ducting.
What was the distance?
Yeah, I'd say it was ducting. It was quite hot days when I was doing it.
What was the distance and what was the power?
Power on the FT230 is 3 watts.
That's brilliant.
So
And distance?
Queensland, how far is, well, he was just on the other, he said he just got back from Mount Warning, so he's on the other side, the Twin Towns. So it's just on the other side of the border.
I think you would have calculated this.
No, I don't remember.
From paper design to fabrication, what sort of time are
But
we
to
looking?
build this,
Well, from designing it right through to fabricating what you have.
Well, research first.
lots of research first.
Yeah,
for a
absolutely.
while, and then just trying to find a material that would work. I mean, the calculations vary too, depending on the thickness of copper, fiber, something. Right? And also affects the gain as well. I'm going to show you.
And there's downtime during the project.
How you like getting sick? Yeah, getting sick.
And does the thickness of the radiator, basically, the wire, does that also affect the bandwidth? Lowest of the other?
Not necessarily.
Really? Okay.
but it can affect your gain for some reason. I don't know why. More research I need to do for that. But as it is, a halfway 2 metre antenna that works, it gives me, try not to trip over my, gives me roughly
Tell you what,
1.5 to 1 on the Hornsby repeater, so that's too much of a Faraday cage in here. Okay, what else is in there?
that's interesting.
I just need to move.
Oh, exactly.
Trust me, I can't pick up anything to make
Yes.
I just want to know if I can do it, that's all. If you see all the other attendants thinking, oh yeah, that's it. But the fact that the thing works, I'm really happy with that. I'm kind of jumping up to joy that it's actually working. I just quickly, Krauss did one study. Somebody help me move this. Yeah, Krauss did on I remember the diagram, I just can't remember how much detail. It was something like this. So I'll start at 4. So that'll be the peak DPI. Now you've got the one wavelength. So, circumference. So that'll be one wavelength. This will be 1.25. There are a couple of curves where he was trying at different frequencies. So, different turns. Now you got 8 turns. It kind of came out like this. 8 turns, one wavelength, would get you about 8 dB.
Sorry, what was the last comment? Would get you what?
8 dB. 8
dB.
8
Sorry.
or something like that.
Yeah.
With 8 turns. So, no, sorry, that was 5 turns, that's right. So that's 5. Then turns would increase as you increase. So the gain would increase as you increase the turns. So that would be 10 turns. The last one that he did, something like 15. So between here and half a wavelength, there's not a lot of difference in it. The amount of gain you get, even though the circumference is smaller. So I thought, okay, I'm going to do it.
Well,
No.
more turns, the bigger the thing. More count.
Yeah, I don't want to do that. I don't want to do that. So halfway circumference simulation, halfway reflected diameter, very expensive experiment, top down before, but not as far as I considered by crowds for the low bands. So originally it's about, before I matched it, about 140 ohms or so, so use a stub or a Helix transformer. You can use some of the high frequency ones and use little matching strips on the bottom of the reflector. So return loss for 70 centimetres is not so good, it's something like 7 dB. But on 2 metres is anywhere from 16 dB to 19 dB, which means that it's about 95% efficient. Because you know all about how return loss works. So you can adjust the turn spacing, get more directivity, that'll flatten out your beamwidth, and you get more gain as well. So inside my house, I can get it summer speed. I can rotate it so there's no signal. I've got a wave meter in my bag, I can show it later if you like. Our standard design, okay. So the design's been around since the 40s. You think, well, the helical is a helical is a helical, but it's not always a helical. Who's heard of the stub helical? That's a USPTO patent. So say you got the circumference this big, and you want something smaller than that. You want to get away with it. What do? You introduce stubs. So virtually the same performance.
Yeah, different design, I guess.
A different design.
Yeah.
What about
It's small.
helical within
It's
the
a,
helical?
what?
Helical within the helical.
No, that's that. Here's the places that's
Compressed.
So it makes it smaller, more compact, more usable.
Yeah, okay.
Anyway,
And is the, sorry, took on.
You make the
you still have the winding,
helical
so it's
to
still
make it longer, but smaller diameter.
smaller diameter. So you can get more turns taken to get more.
Yeah, not a spiral, which is
It'll
spiral.
still be a spiral. So that's your normal one. That's how you measure your circumference, where it meets up there. So in the stub, it's going to continue along. It'll have,
Is the regularity of those stubs critical?
it can be.
Yeah.
I don't know enough about it. I've got to read through the patent.
Right.
Patent's been around for about 20 years.
There could be another thought. What about surrounding the wire and the helical with, say, a dielectric material to reduce the velocity? Say you use, say, inch diameter Teflon around your 8-inch diameter wire.
You should try it.
So down the bottom, I was in the park testing this. There was a park ranger there. The signal was over there. Park ranger happened to be there just as I said. He said, "Oh, what are you doing?" I did that. I looked past the reflector. He was gone. Where the hell did he go? Did he run off or something? So that's a good thing for a park
He would
ranger.
be in the line of the disruptor ray.
Does it work on parking, please?
Oh, wish. Put this on top of the car.
You know there's a big market for this in the movie industry.
Yeah, there's a thought. They're not really Helix, it's just out of a movie called versus the Flying Saucers from 1950. It's just for fun. So there you are. Any other questions?
Oh.
It's missing the big industrial mansion.
Oh, they came out of the demolished hotel.
Okay, the question, you were talking about a right-handed polarised helical to a right-handed polarised helical at each end.
Yeah.
How does it work if the other end's got just a linear antenna, either horizontal or vertical?
It'll receive it okay. It's when you have a left-hand polarised, it doesn't receive it. The left hand doesn't receive it as well as a regular antenna. It wouldn't receive the right-hand polarisation.
Now, why are they used for satellites?
Because they're very direct.
Okay?
You can get a very narrow beam, so they're very direct. You can pinpoint satellite and you can track it.
Satellites also tumble, like with our amateur satellites. So obviously you don't have to bother with rotating your aerial if you've got a circular one.
Sure. Let's have something in the right direction.
It's traveling in the right direction. And I've got to say one other thing, I don't think I've said this. These are not resonant antennas. There's a bit of hoo-ha about resonant antennas because you only get a resonant antenna on one frequency. Sure, you can get the other one. This will never be quite a resonant, but you'll get pretty broadband flat PSWR on it anyway. So there you are.
Could you use tubes without a decent plate?
Yeah. Yeah. I've seen people get thick pipes, thick PVC pipes, and just wrap it around the pipe.
Yeah, 110 mil height is very good in 23 centimetres.
Yeah, exactly. So for 2 metres, that's a bit ridiculous. So there you are.
So you just use straight on the tube, Teflon line, coax.
Yeah, you can do that. Yeah, it's a short feeder for them.
I think this.
It's been on the bench here, like that.
Oh, that. That's got a joiner in there. So it's going right in many rods. It's going there.
Oh, I see.
That's all that is. And it's solid.
Yeah,
Yeah.
take it to
Need a super hot soldering station.
Wow.
There you are.
Thank you very much.
Fun, huh?
Brilliant.